8.4 Notes, Part 2, Example 3. In a study of 150 randomly selected occupants in passenger cars and 200 randomly selected occupants in pickup trucks, 86% of occupants in passenger cars and 74% of occupants in pickup trucks wear seatbelts. At alpha equals 0.10, can you reject the claim that the proportion of occupants who wear seatbelts is the same for passenger cars and pickup trucks? So what I would like to do first is kind of separate things out just a little bit. So I'd like to underline what is for sample 1 versus sample 2. So I'm going to let my red represent the number of occupants for the, pickup trucks. I'm just kidding, passenger cars. And then my blue is going to be for my pickup trucks. So my N1 is equal to 150 because that's how many we had for passenger cars. And then my P hat, so that's P for 1, is going to be 0.86. For your N's, for N2 is going to be 200. And then based on that, the P hat for 2 was given as 0.74. Okay, another thing that I can kind of derive from this, because they're not really saying explicitly, but we also need the X values for each of these. We also need the X values. So how do I find that? Well, if I know that there were 150 people and 86% of them said that they do wear them, then my my X is going to be 150 times that number, that percentage. 150 times 0.86. So 86% of the 150 people said that they wear seatbelts. So 150 times 0.86, when you multiply that out, you get 129. Those are for your X values. So then to find the number of people that wear seatbelts for pickup trucks, I'm going to take the total, which was 200, and I know that I need 74% of that number. So 0.74 times 200. When you multiply that, you get 148. This information is going to help us a little bit later on, but it's kind of just easier while it's still fresh and while we're identifying information to kind of know what goes where. So I'm going to also tell you all that if you are working out problems like this, you can go ahead and assume that the N times P is greater than or equal to 5 and 1 times Q1 and so on and so on. So if I give this type of problem, assume that it works unless I'm asking you to show whether or not you can. So part A, they would like for me to identify the null hypothesis as well as the alternative. So the claim we kind of underlined a little bit. They're saying that the proportion is the same. So they are saying that P is equal to P. But what P's are we talking about? Well, the P1 is the same as the P2. That's the claim. So let's go ahead and label it claim. And then so the alternative would be that P1 is not equal to P2. And we're going to assume that this is true usually when we set up our stuff. So the next thing that I would love to do is to find my critical values. And whenever I see critical values, I automatically kind of think about my bell curve. Now, because we're looking at an equal to or not equal to, we know that this is going to be a two-tailed test. We're given that alpha was 0.10. So if you're looking at it on that table, you're looking at the 90% level. So if you go up or back for you, you're looking at a 90% level. So that means you're looking at the positive negative value of 1.645. 1.645. So this is your reject, and this is your reject area. Those are critical values, so anything that's going to be less than this or greater than that, you're going to reject. So any z value that is less than negative 1.645 or that is greater than positive 1.645, that is where you're going to reject. Okay, the next thing I need to do is to find my z value. So that's what I'm going to be looking for here. Let's remind ourselves of what our formula is, just because I think it'll be a little bit helpful. Okay, so we have our formula, z equals p hat 1 plus p hat 2. That's the first thing I see. We were given those in the beginning. So here's my p hat of 1 was 0.86 minus p hat of 2, so 0.74. Then from that, I'm going to subtract P1 minus P2. Well, remember, we're assuming that P1 equals P2. So if they're equal to each other, then when I subtract them, I should get 0. Like if this was 0.5 equals 0.5, well, what's 0.5 minus 0.5? 0. Always going to be a 0 there. And then you have the square root of. Now what I need in my life is the P bar and the Q bar. So we found that in a previous one, and we're going to use the same exact setup that we used before. So for our P bar, we have the formula x1 plus x2 over n1 plus n2. So let's plug in our values that we know from the very original. So we have our n1, x1, and we have our n2 and our x2. We're going to plug all of that information right into here. So that's going to look like 129 plus 148 divided by 150 plus 200. So this is 277 divided by 350. So my P bar is equal to 0.79 approximately. And so my Q is going to be 1 minus that. So that's going to be 0.21. Okay, so we're going to put that in right here. My P bar, 0.79 times 0.21. We're going to multiply that by the square root of 1 over n1, so 1 over 150, plus 1 over n2, so 1 over 200. Then you're going to use your calculators, and you're going to get a z value of 2.73. So z equals 2.73. Well, where is that? Bummer. My bad. Here, it's in my reject area. It's a big fat reject. So I'm going to have to reject the null hypothesis. And our null hypothesis, don't forget, was that they are equal to each other. That's my claim. It's not the same for people that drive pickup trucks and passenger vehicles. So for our interpretation, at the 10% level of significance, there is enough evidence to reject the claim that the proportion of occupants who wear seatbelts is the same for passenger cars and pickup trucks. There is your lesson for today, and have a good one. Bye-bye.